Hi folks, okay, welcome to our IGOR 2 video instructions. I'm gonna start us off with a little bit of whiteboard action. I'm gonna do just a very brief lecture that's gonna lead directly into how we're doing this analysis, okay? So, I wanna remind you, we've got a few relationships that we've discussed and stuff you've already been playing with in your exam one, okay? So I'll remind you delta H. To calculate delta H from data, okay, we can use a thermogram, right? So in that thermogram, remember, is our CP versus T, right? And you've already been playing with some data that looks like something like that, right? And we did this best fit analysis, right? Something like this. We're going to keep playing with that. All right. And so if we want to extract delta H from this value, we remember that actually we can do that by taking CPM times delta T, right? Simple as that, okay? So now that's in the case if we have a constant heat capacity, okay? Which is a fairly reasonable approximation. However, if we have some data, like, all these lovely data points, and that helps us generate this smooth relationship, right? What we get out of that is some function CPM as a function of T, right? And in that best fit line, you use that standard equation that we've talked about, the A plus BT plus C divided by T squared. Whatever equation we're using, we know that it's a function of T. So now I can expand on this, right? And if I integrate from some initial to final condition, my fit function, then I will get the delta H, okay? So in other words, if I take this best fit line and integrate it, I'm gonna get delta H versus T, okay? And it's gonna look something like this, all right? And so now what that allows me to do when I consider the T initial and the T final, right, and plugging in everything here, for now I'm just gonna leave this integral as is, but I'll substitute it into this delta H. We would have H of T final minus H of T initial equals this integral, okay? And so what's important to note, if T initial is 0, if we actually get data all the way down to 0 Kelvin, then we will have a true representation of delta H, okay? But suppose we can't get down to 0 Kelvin. Suppose my, I'm just gonna pick a random number. Suppose my T initial is 78 Kelvin, okay? So then technically now, if let's say I want to know, well, what's the enthalpy at 298 Kelvin? So in other words, suppose now here is my very first data point at 78K, okay? Which means, technically my fit equation might only be reliable starting at 78K, right? I don't know what it is all the way down to 0. But now suppose that I want to know the enthalpy at 298, right, my standard enthalpy, then we have to recognize if I start at, let's say, 78 or whatever I start with, if I don't start at 0, then technically I don't have the true delta H. I have the H, I'm going to write this in a subscript, or superscript, that's kind of the standard convention. I technically have H at 298K minus H at 78K. So my delta H is actually off by a little bit, okay? So we have to figure out what to do to get this thing all the way down to 0 Kelvin. And one of those things that we can do is fit a line all the way down to 0 and hope that we can extrapolate down to 0 and it remains to be fairly accurate, okay? So that's for delta H. So there's another analysis that we can do for delta S. Okay, and so we remember delta S is the integral of T initial, T final of dq divided by T. Well, I remember that at constant pressure, dq equals Cp dt. Okay, so now if I want to get molar entropy from my heat capacity data, then I can perform the same integration that I just described. However, it's going to be Cpm as a function of T, but now divided by T times dt. Okay? And so there's a number of things I can do, but one of, I think, the most straightforward is now, if I were to take my thermogram, but then divide all of that data by T, you know, it's going to get some kind of curve, right? And if I fit this now to a best fit line, you know, something like this, all right, then now that's going to give me this new fit function that I'll call Cpm of T divided by T. You know, technically it's just all one new fit function. I'll circle that whole thing, right? And now if I were to integrate that fit function over some limits, that would give me the delta S. And of course, the same situation applies. In other words, if I want a true third law entropy, right, then I recognize what I really need is the molar entropy at 298 K minus the molar entropy all the way extrapolated down to 0 Kelvin. Okay, so let's do that. Let's get into that. And I'm going to demonstrate for you on the data set that I gave you in that IGOR 1 assignment. Okay, let's minimize this. But for your assignment, you're going to use a new data set that I send you. Okay, so now I've just opened up that IGOR 1 assignment, and I'm only going to extract the data that I want. So I put all of my data in a table so that it wasn't all floating around. So I'm going to say convert. Let's see, did I get that data table? There it is. So I want to play with this data. I also want to play with this curve right here. So I just said convert to object so that now I can, oh my goodness, I'm screwing all kinds of stuff up here. So that way I can actually edit it. And so this is the only data that I want from this file, all right? So I'm going to kill this thing. I'm going to kill this thing. I'm going to get rid of all of this stuff to make my life a little bit easier. So I've got all of these things. And so now I'm going to say, IGOR file, save a new experiment. Okay. And let's see, I'm going to call it IGOR 2. I put this little working file thing here. And that allows me to recognize that this is like a draft that I'm working on. And here I've got my data browser. My data browser still has a whole bunch of that data from the other experiments that I didn't need. So let's get rid of that stuff too. So I can say kill waves. I'm just going to get rid of everything that I don't need for this entire experiment, okay? So I've got to make sure that I don't get rid of, oh, and you know what's cool? So you can only kill waves, see waves not in use. So actually, I don't even have to worry about picking out that T and CP because it's in use. So I can literally select all of these things and say, do it. And I just, see, look, here's the command, kill waves. I got rid of everything that's not the thermodynamic data. Okay. You're going to start a new fresh file because you're going to use different data. But all the same, I wanted to be able to quickly show you what I got going on here. Okay. So now, what I can do right away, because I noted from my file that if I integrate this function, CP versus T, that's going to give me the delta H right away. However, I'm not happy about how this fit doesn't quite go through 0 because I want a true third law enthalpy and entropy calculation. So I'm going to play with this a little bit. Instead of using that heat capacity equation that we talked about, and I'll show you just why in a second, why I'm going to use a different equation, okay? I'm going to put the error analysis, confidence bands, and I have to do these initial guesses, right? 1, 1, and 1, and I say graph now, and it's all crazy. But now I'm going to make the A be forced through 0, and I'm going to push do it, and yes, you can see that that's not a great fit. And it's not a great fit because of that C constant. That C constant is C divided by T squared. And when T is 0, you can't have 1 over 0. So this equation is just not looking good for me, okay? So I played around a little bit earlier on with some of these other prepackaged equations in here. And this Hill equation, I know when you look at this, this looks crazy. But part of data fitting is just kind of playing around with equations. We call this massaging the data. And I want to also play with this in a way that it goes down through 0, so that I have a true 0, 0 data point, or at least I get a fit through 0. Okay. So on my coefficients, I can see that this base term is going to take on the effect of a y-intercept. So I'm going to force that to be 0. Okay, and I've got all my confidence bands, I've got all this stuff, so now I'm going to say do it, and hey, that's nice, right? That's a much nicer fit, and actually if you look all the way down here, it looks like it's going through 0, so that's pretty awesome, okay? So now let's do this thing. So I want to integrate this data to extract the delta H. So here's how I can do it. For one, I note that I could have taken this equation and throw it into Mathematica the same way you did in your exam 1, and that would certainly give me some values. But I want to do this in IGOR because I want to do it graphically. Okay, so check it out. Under the analysis menu, I'm going to say integrate. There it is. All right. And what I want to integrate now, I don't want to integrate my data. I could, but what I want to integrate instead is my fit. That fit underscore CPM, that's the automatic wave name you get when you curve fit, okay? I want to fit that equation, or I want to integrate that equation. And I'm going to say fit CPM versus calculated, because it's a user-defined equation. I'm going to use the trapezoid method, and I'll talk about that in just a little bit, why I think that's a nice method. And on my auto wave, I'm going to say, yeah, we'll say auto, that's fine. And then display output wave in new graph. And then let's say do it. And oh, it went back there behind me. Oh, and look at that. Cool. Believe it or not, this is H as a function of temperature. Totally awesome. It's as simple as that. That's literally all that I had to do. Okay. So I'm not going to spend a whole lot of time on this video formatting this. You'll need to do that correctly for this exercise. But I'm just going to add a few pieces of information so that when we're looking at it, we know what we're seeing. I'm just going to write enthalpy. Let's make all of this just a little bit bigger so that we can see what's going on. Okay. Oops. Let's see. And you notice now also, so let's label the bottom axis to temperature, I can't spell, in Kelvin. And then now this is a cool trick that I can do. Notice my values here, 30 times 10 to the 3. That would be 30 kilojoules. So keep track of these units, right? So because the CP was in joules, this is still technically, 30 times 10 to the 3 joules. It's 30,000 joules. But watch what I can do in IGOR. I can make it do unit conversions for me. I'm going to go to scientific notation. Oops, not on the bottom axis, on the left axis. So scientific notation, now it says it's 3 times 10 to the 4. And I'm specifically going to say minus 3. And the reason why I'm going to say minus 3 is because that's the relation between a kilojoule and a joule is either 1 over 1,000 or 1 times 10 to the minus 3. And now on my access label, I'm going to note that this is in units of kilojoules per mole. Pretty sweet, right? I can see that 30. Now that's 30 kilojoules, which is 30,000 joules. Okay. And I'm just going to leave it at that. I'm just going to leave this graph simple. You'll want to format this. And let's give that a nice thick black line. But now, how can I use this same program to do the error analysis in this determination of enthalpy? Well, I can repeat the exact same thing I did, but now I'm going to integrate the confidence band lines, which is super awesome. So that's not as straightforward to do in Mathematica. So analysis, integrate, and that's why I like doing this in IGOR. Okay, so now what I want to integrate is, don't worry about this X wave. The X wave is going to stay calculated. There's my upper confidence. So it goes, the wave name was CPM. So the data fit, the middle line right there, that's fit underscore CPM. And then LC is the lower band and UC is the upper band, or lower confidence, upper confidence. Let's do the lower confidence. And now versus calculated, trapezoid method. And now I'm going to display it on the top graph. So it's going to automatically put it on this graph that's selected. And I'm going to say, do it. Cool. There it is. So now let's repeat the same thing for the upper limit. There's the upper confidence band, calculated, auto output wave name, trapezoidal, top graph, do it. Awesome. That's really cool, right? That I got those bands. And actually, it doesn't look too bad, right? My error there. So now let's blow it up. So how would I report then any one enthalpy value? Well, check it out. There's a really handy thing you can do for Mac users. It's Command I. For PC users, I think it's Control I. Or you go graph show. Right now it says hide info. I'll say hide info, see it, put it away. But I can say graph show info. And I realize that this is going to be really small for you to see. Okay, so you'll have to hunt and peck on this on your own computer. But now I'm going to grab this A cursor, and I'm just going to put it on my best fit line right there. Oops, sometimes it goes to one of the ones you don't want. Get on there. Okay, well, so what I can also do, if it's not going on there, so you can see A cursor, it's on the upper confidence CPM integrated. That's what all that says. I can right click, and I'm going to put it on the fit line. There it is. And I'm going to now, I can check this out. I can use the arrows, and I'm going to navigate all the way up to, let's just say, 200 Kelvin. Because let's suppose we wanted to know the delta H at 200 Kelvin. All right? Well, there it is. Look, I put my data point at 200 Kelvin, so I know that this is small for you to read, okay? But I put that data point at 200 Kelvin, and look, that's the enthalpy value. It's 32280, so that would be 32.28 kilojoules. Awesome. Right there, graphically, I've got the delta H without having to actually calculate anything, right? I did it graphically. But now, how do I get the error out of this? Well, this is pretty cool. So now I'm going to, what I do if I want to hold this arrow, so notice that like it's free to move around, I uncheck that box, and now it's frozen. I'm pushing my arrow keys, and it's frozen at these two values. So now my B value, I'm going to turn on, and I'm going to drag it somewhere around there. And I'm going to get it to that same temperature, fantastic, 200.1. And now look at this. It not only does it tell me what then the value is, right? So here for the fit, it was 32.280 kilojoules. For the upper band, it's 32.90 kilojoules. But then look, it actually calculates the delta Y for me. So what does that delta Y represent? That represents the plus portion of the plus or minus in my data. That's awesome. So I'm going to try to remember these, or actually I'm going to write them down here, and then I'll put them in my, I'll write them down on that board so you can see how I report it. So let's see here. Scrap piece of paper. I should have had one ready in front of me. So I'm seeing that it's 32.280, and the upper band is so 621 joules. So that would be 0.621 kilojoules is my upper limit. And the way that I can get my lower limit is now on this B cursor. I'm going to right click and move it to the lower confidence band. Hey, look at that. And it went negative 621.48. So that's awesome. So now I can see that, oh, I lost my whiteboard. In any event, I would then go and if someone wanted to know what's the enthalpy at 200 Kelvin, I would report it as 32.280 plus or minus 0.621 kilojoules per mole. Okay, awesome. And I can make a nice, like, pretty looking graph out of this thing, right? I'm not going to do that. I want you to do that for the assignment. And also for the assignment, I'm going to ask you to calculate the standard enthalpy from a data set I give you. Standard meaning at 298K. This data set that I have here doesn't go all the way out to 298K. So that's why I just kind of randomly grabbed a data point at 200. Okay, well, that's cool. So that's all the enthalpy. So we're all good there. And, you know, if I wanted to clean this up a little bit, you know, like maybe instead of saying enthalpy, I could say like delta H or something like that. Do you know what I mean? So I could, you know, follow kind of the guide that I've been giving you, like make these things look nice and make them unique. Okay. So now what about entropy? Well, check it out. I'm going to open up really quick an Excel file. All right. And I could do this type of analysis in IGOR. You know, IGOR has these spreadsheet capabilities, but I'm also just going to show you how easy it is to go back and forth between Excel and IGOR. So all I did was just a Control-C, Control-V. Excel isn't so good at recognizing the wave header names. So you notice that it just took the data in there. But what I want to do now is get CP divided by T so that I can do my entropy calculation, right? So in Excel, on this column C, I'm just going to say equals, and I'm going to say this value divided by this value. So that's my CP divided by T. I'm going to push enter, and then so you can see it says equals B divided by 1. I'm a big fan of having a nice organized spreadsheet, even if this is just a demonstration. I think this is nice to have some organization to this. And so I'm going to say that's CPM divided by T. And now look, I only did one data point there. There's a really handy trick in Excel. So notice when this goes black, the arrow went from white to black. When it goes to that black color, I'm going to double click and bam, it filled everything down for me. And look, it did the exact formula that I needed, right? It calculated all of those things. And now I'm going to take this, I'm going to grab that wave name header. I'm going to say Control-C. I'm going to go back to my IGOR, Control-V. Nice. I'm not, it said CPM underscore T, so it didn't like name it perfectly. So I would need, for my own cognition, want to, recognize that I'm going to have to like keep track of what CPM underscore T is and what CPM T is. Of course, I can also just change the wave name. And I can actually do that here in my data browser. So there it is. Okay, there's that wave. And I'm going to push this edit button. And I'm going to call it, can I say CPM divided by T? I did, great, it took it, CPM/T. And notice it puts quotes around it, so maybe it doesn't confuse it for a mathematical operation. All the same, there it is, okay? And so now what I'm gonna do, I'm gonna make a new graph, and I can do that by saying display, quote, CPM divided by T, quote, versus T underscore K underscore. I hope I did this right. Oh, wait a second. Maybe I put that slash by accident. Oh, there we go. Did I do it correctly? Hey, sweet, I did. Okay, great. Right, because I can tell there's my temperature scale is on that x-axis, right? And remember, I know we did a mathematical operation. We took the data points divided by t. This is still data, okay? So I'm going to make it markers. Let's go with upside down triangles. I like size 3 with the stroke color. Let's make it purple. Okay, great. So there's my data points, okay? And I'm just going to do a real quick set of labeling on this thing, just so we know what we're looking at. Okay, so bottom, that's temperature in Kelvin. You know, it's important, I think, add these labels, even if you're not gonna format it. You know, you do want to know what you're looking at for your own records. Okay, so there I said CPM divided by T, and of course, when you go to do this for your assignment, I want you to make nicer looking graphs, right, for your presentable file. And let's make the access range. I'm going to make it so we're going from 0 all the way to 200. And in the left, I'm going to say 0 to, like, 2. I like getting these nice even numbers so that I can, see my range and stuff. Okay, great. So now what I want to do is fit this data the same way that I fit the heat capacity. Okay. And admittedly, I had to play around with this quite a bit. It was a little challenging for me to find an equation that I liked to fit this. And you might have to do that with the assignment that I'm going to give you. You might have to kind of like pick through some of these datas. For this, or pick through some of these equations rather. For this one, I'm going to pick a polynomial, okay? And I'm going to make sure that I'm fitting it as CPM divided by T versus T, right? And I also, because I want to do a proper third law analysis, I want to make sure my equation does get all the way down to 0. So on these coefficients, if you notice here my polynomial, this K0 is my y-intercept. So I'm going to hold that value at 0 so that I know this data goes through 0, okay? And we'll say X range, 95%, confidence interval, confidence bands, do it. Oh, that's terrible looking. Oh my God. Okay, so let's play with this some more. Don't make this your final product. If that's what your fit looks like, you might need to play with it. Let's add a fourth polynomial term, okay? And let's hold that at 0. Let's see. Okay, that's slightly better. So I will tell you, for the purpose of this exercise, I'm going to proceed with this. Okay, this is not physical, and I hope that you can tell that, right? Because of the way that this like goes up and then it goes down, and then you can see that the error is getting humongous. Like, look at how big the spread is in those confidence bands. It's not great. The data set that I'm going to give you works really nicely. You can get a nice fit out of it. And I'll caution you against using polynomials. Polynomials is kind of like your last resort if you can't make it work, because a polynomial will do this kind of almost sinusoidal pattern. So this equation that I used right here, the Hill equation, I'm going to change the name of that, okay? That's a pretty good one for these types of datas, but play around with all these equations, okay? And then now, just so I kind of can visually see what I'm looking at, I'm going to make the fit line just a dark color so I know that that's the fit line in the middle. And now I'm going to repeat the exact same thing that I did over here. Let's get rid of that info. I can do that by saying Command-I. So I'm going to do the exact same thing that I did, but now when I integrate CP divided by T, I'm going to get entropy, okay? So let's do that. So let's say analysis, integrate, okay? So now I got a whole mess of data here, so I got to make sure that I'm picking the right thing. So I want it to be the fit equation, right? I'm not going to integrate the data points. I'm going to integrate the fit equation. And it's the CP divided by T versus calculated, the trapezoidal, I'm going to make a new graph out of this, so I get a new enthalpy graph. And let's say do it. And there it went behind my thing. Okay, that's not bad. That's about kind of what I was expecting to see, right? A steady increase in entropy with an increase in temperature, which is exactly what we would expect, right? As we increase temperature, we expect to have more microstates. We know from the statistical description of entropy, with more microstates, entropy should increase with increasing temperature. Beautiful, we see that. Awesome, okay? And so now let's make that one a dark color. And we know, I know that represents my molar entropy. So I'm just gonna do a quick and dirty label name, entropy. And that has units of joules per Kelvin per mole. So again, this is not like a presentable set of things that I'm doing for this access, right? I'm just kind of labeling these so I can see what I'm looking at. Okay, so now, and notice here with entropy, entropy is typically, doesn't need to be in joules because entropy values are smaller. So these numbers here, I'm not going to do any kind of exponential prefitting or whatever like that. I'm just going to leave it as is, okay? And now let's do the error analysis. So now I'm going to say analyze, integrate, and now I'm going to integrate my confidence bands. So there's LC CPM divided by T, so that's the lower confidence band, calculated, trapezoid. Now I'm going to display it on the top graph. So when you say top graph, you have to make sure that this graph is selected. So can you see how my other graphs are kind of grayed out? This is the graph I want it to go to. And let's say, and so first of all, I kind of expect there's going to be more error from this, right? Because this fit wasn't as good. So yep, and we see that. And now let's do the upper confidence band. So I'm looking for UC. Yes, here it is. Yes, okay, I was confusing myself. So you got to keep reminding yourself what it is that you're looking for. UC underscore CPM divided by T. Don't do this UC. I was looking at this UC CPM int. That's from my enthalpy calculation. We're doing our entropy calculation. Okay, so UC upper confidence band of the CP divided by T, calculated, auto, trapezoid, top graph, do it. Awesome. That's what I was expecting to see, some kind of spread in my values, okay? And so if I go back, you know, this one we did pretty good, right? This was 32.28 kilojoules plus or minus 0.62 kilojoules. Let's see how we're doing right here, okay? So I'm going to move the cursor. Let's just do it at 200 Kelvin like I did before. Okay.
Dad, are you practicing?
No, I got my son here asking me what's going on, and I'm recording a video. No, buddy, give me just one more second, okay, buddy? Okay. Just wait. Okay. So, oh, you know why? Because so I had this fit only from 0 to 200, but on here I had it fit from 0 to 220. So don't worry about it. I'm just going to grab the data from one. Oh, there it is, 200 Kelvin. Okay, great. Okay, I was looking at that X data point. But there's my X value, 200 Kelvin, and it's 300.08 joule per mole K. Okay, so I'm going to leave that one on there. I'm going to take the B cursor, and I'm going to put it right there, and aha. So I know that print is small, but check it out. There's a much bigger error there, right? So it's saying it's 300 plus 19. Let's look at the minus. It should be about the same. But just to make sure, I'll switch it to the LC. And yep, it was minus 19. So now this entropy is 300. Let's call it 300.1 plus or minus 19.0. Okay? And of course, that's the molar entropy at 200 Kelvin. What I'm going to have you do in your assignment is analyze a new data set and get the standard enthalpy and entropy out of it, okay? And you're gonna end up with 4 graphs. The 4 graphs you're gonna end up with are your enthalpy, entropy, CP versus T with this, better fit, and CP divided by T versus T, okay? And I want you to make a nice layout with all 4 of those in the same graph with a little figure caption, okay? And in your little figure caption, or actually, put this into like a document just like you've been doing and write me a little paragraph that just tells me what your reported standard molar enthalpy and entropy is with the plus minus limits that you find. Okay, folks? Happy data fitting, integrating, and thermodynamic analyzing. I'll see you at our live meeting on Friday.